welcome back to part 13 of Password Cracking 101 plus 1. In the last video we used prints to conduct a passphrase attack with space delimiters based on our Google word list, which is on your Kali boxes. To do this, we first of all inserted a space at the end of every line inside our Google word list to create a delimited dictionary. We then used prints over our word list with a space in it, setting minimum and maximum element counts of 4, because we were attacking a 4-element passphrase, setting minimum and maximum password length parameters as per the objective, and then using hashcat to attack that, deleting the last trailing space from our word lists. We can use this to attack space-delimited passphrases quite nicely. Of course, though, as always, it depends on the quality of your list and the time available you've got to you. We're going to move on to look at a couple of other different attacks, and then on to some crypto and non-ASCII based attacks as well. So, Purple Rain. NetMux has not had a mention yet in this training, but NetMux certainly deserves a mention now. That's NetMux on Twitter, and NetMux is also the author of the Hashcrack book series. Highly recommend you pick up a copy if you're a password cracking enthusiast. NetMux found that when you shuffle the input of your word list, you shuffle your word list and input, you get different output each time. So this is like fully non-deterministic stuff now, and we have no idea what's going to be generated before it's passed off to prints and other things in hashcat. In the examples shown here, you can see that RockU is being shuffled before its input. If you take RockU, the first 10, 20, 100 entries of RockU, or any dictionary, whatever you want to do, take that into prints and then look at the output, it'll be the same output each time in terms of the order, it'll be a fixed output. But if you shuffle that input list first, it generates completely different output every single time, as sort of shown here on these few runs on the slide. So simply by shuffling that, you can just generate completely random candidates each time, which is fantastic. This is sort of fully non-deterministic, infinite runtime now. It's a case of running hashcat, and then after 2, 12, 24 hours, however long you're willing to give it, Control-C, start again. And every time you run, you're going to get completely different candidates. So, this is a really quite a sort of like a crazy attack, and certainly a fun one to leave going if you've tried lots of other things and have had no luck. I always like to look at the candidates that Hashcat is generating each time when you get the status updates, because some of it is just absolutely inconceivable. So, shuffle your word list, pipe it to prints, pipe it to hashcat, and throw some self-generated rules at the end. Why not? Or your rule of choice, or anything else for that matter. Till the Sun Burns Out by EvilMog. Okay, so another member of Team Hashcat here. I didn't find terribly many references to this online, if I'm honest with you, but this is referenced in the Hashcrack book I've just alluded to by NetMux. This combines several things, and with a little dose of insanity at the end there as well. By the looks of it, prepare isn't really used. Prepare is a dictionary optimizer for the permutation attack, as described on the Hashcat wiki. But it seems to be a little bit redundant in the attack chain here. For what I've seen, it generates the same things. It ends up with the same results as if you just use permute by itself. We'll have a look at an example in the next slide. But this takes this dictionary optimizing binary prepare, pipes into permute, which produces all possible combinations of a given word. Then it's expanded. Then it's piped to prints. Then it's piped to hashcat. So like I said, a little bit of insanity there. You can see here what I've done just to sort of show is we started with just a few vanilla candidates from RockU, ran it through permute, and you can see what it starts to do. It starts to sort of chunk this up and give you all possible combinations of that candidate. However, preceding that with prepare first, as shown on the right here, actually didn't do anything to the number of candidates it generates. And after you've sorted that, the hashes match of both those files, so it's the same content, not just the same number of lines as well. So it did seem to be a little bit redundant. However, having said that, you can produce some really weird and wonderful things feeding that attack chain in. So this is about really now getting creative with Hashcat and just looking for ways to generate candidates that you just won't get with dictionaries and rules. Okay, I've got a video where there's several of these attacks, including sort of fingerprint and prints and other things, all built into one across a data breach that I did at a conference talk a few years ago now, but the video is still good. And after the video, because there's a lot of numbers, so it might be hard to follow. We do have a slide showing the statistics of what happens. You can see the success rates of each of these attacks in situ. So we're going to start with an empty pot file here, just to sort of show that we're starting from nothing, we're starting from scratch. The first thing we're going to do is we are going to identify our dictionary, which is going to be the last FM data breach from a few years ago. Just take the top 500,000 hashes from that. These are MD5s, and we're going to start off with my go-to for fast hashes, which is RockU with my one rule to rule them all. That's going to run through, and it'll probably finish fairly quickly. Oh, yeah, I've edited some of this out. You can see here that we have managed to crack, recovered 290,000 there, so 80% straight off the bat, and that's after deduping as well, because there were duplicate hashes in that word list. We're now down to 68,000 already. We're then going to actually do a brute force attack. So this is in preparation for a fingerprint attack. But rather than look at our pot file, we're actually going to generate our own dictionary by conducting a brute force attack. So we've got 5 question mark A's here. So that's 5. It's a 5-character brute force effectively. Any 5-character password using the 95 principal ASCII characters there, and we're going to generate a list called word.list. We're going to do that, run that over the remaining 68,000 hashes or whatever it is left, and we can see that we've managed to recover 52 passwords. So 52 passwords in that remaining list are 5-character passwords, as shown here. With just those 52 5-character passwords, we are then going to prepare our fingerprint attack. And because these are all MD5s, a simple cut on a dollar delimiter will be fine. We've got no crazy hashes in our pot file that's going to ruin that. We're going to take that, expand it, unique it, and create a dictionary that we're going to call word.list2. Then by running that in combinator mode with itself, this is the fingerprint attack. We're removing the hashes each time from this successive run, because we're doing quite a few runs here. There we go. That's now cracked 615 further passwords by running that 5-character brute force dictionary in combo with itself. Repeat and rinse. Take word list 3, expand it, unique it, create word list 4, and then word list 4 is going to be running combo with itself and producing the output of word list 5. So any cracked hashes are going to go into a dictionary called word list 5. I think we're probably going to fade to black and then come back in a minute, because there are a couple of these, and as we'll see, the graph goes up and down with fingerprint attacks before you eventually tail out to nothing. Okay, so now we're going to move on to prints. First thing we're going to do is we're going to run prints using RockU, minimum length of 8, by itself. So nothing special about this, we're just going to use prints on its own over the RockU dictionary. And for these, I'm just doing 2-hour sprints, because these would have kind of gone on forever. So I'm just trying to do this 2 hours at a time. We recovered 82. Okay, not fantastic, but we'll now see down the bottom. We're now going to run a print optimized rule over that. So the same thing again, but we're going to use a rule, and you'll notice even just by applying a rule, we're getting some fantastic candidates coming back from here, and nearly all of these are actually space delimited as well. So we've not done anything. We've not faked this. The dictionaries haven't been edited. This is all starting from the vanilla RockU dictionary in this particular case for the print attacks. So by running prints with rules, we're generating clear text candidates that are phenomenal. They're really, really good, and this is from a real life data breach. Okay, this is from the last FM data breach, so the hashes haven't been sort of edited or faked either. Running that through, we've now managed to crack 3,325 further MD5 hashes. We are now going to do a purple rain attack. So, as alluded to by the attack from NetMux earlier, instead of just putting prints, RockU into prints, we're going to shuffle RockU first, pipe this into prints, then give it to Hashcat, and we're going to generate 300,000 random Hashcat rules as well. We're going to let that run for a couple of hours. And there you go, and you can already see that it's, again, starting to generate some pretty cool password candidates with some weird and wonderful special characters. We've even got some, I think, some umlauts here, some accents over the O as well, so we're really starting to branch out and generate these really interesting candidates. Okay, at the end of this, we are going to have cracked a further 4,000 passwords. I think we're just going to run the same thing again, yeah. Another shuffle of rock queue. We're going to run another Purple Rain sprint there with 300,000 self-generated rules. I could have let this go on for more. I could have, I could have stopped it, and I did stop it. It's just to really show that you are going to get different candidates each time. And it was just to make sure it was consistent with the 2-hour sort of runs I was doing this initially. Now, only another 1,600 hashes, but this time, for this last one, we're going to take a Purple Rain attack, so we're shuffling the input list, but this time we're going to apply one rule to rule them all over the top of it. Okay, so that's going to start running. That's going to run for 2 hours again. And that cracked 7,000 hashes, so another great big jump up there, which is brilliant. So that's the end of the video. And if we move on to the next slide, because there was a lot going on there and a lot of stats on the screen, this will hopefully make it a little bit easier to understand. So we took the top 500,000 MD5 hashes from the last FM data breach, and even when that was deduped, that got us down to 358,000, a little bit more unique hashes. So there was already a fair degree of password reuse in that top 500,000. So starting with this 358, a rock queue and one rule immediately, well, I say immediately, very quickly, within a few minutes, had cracked 80% of those hashes straight off the bat. We then prepared our fingerprint attack by conducting a 5-character brute force. Now that 5-character brute force cracked, I think it was 52 passwords, and then expanding and uniquing that, running that in combo with itself for fingerprint, cracked a further 615. These are percentages of the remaining hashes each time, not the original total number, of course. A few more fingerprint attacks. You can see how, like I said, the kind of graph would go up and then down. So the fingerprint 1 gave us 615, the next attack 9,000, and then a little bit lower, and then lower, and then lower, and lower still until we hit 0. But again, if we weren't trying these attacks, we might have missed these attacks. We might not have cracked these hashes if we hadn't been looking to branch out above dictionaries and rules. We then started some prints runs, prints by itself, prints with its optimized rule, and then we started Purple Rain attacks with 300,000 hashcat self-generated rules, and then finally we wrapped up with another Purple Rain with run rule, and that cracked a further 7,000. Now these ones that were in the pot file were actually because I was a bit slow to the keyboard, or I must have gone for an extra long coffee, because sometimes it was either a little bit past 2 hours, and when I hit Control C, the password rig was running so quickly that even though I killed Hashcat, a few hashes occasionally I saw crack after the stats had completed. So I'd press Control C, the Hashcat session would end, but it would spit out a couple of hashes that were sort of mid-crack, half-time, sort of halfway through. So there are a few remnants here that we'd seen in the pot file, but by and large, the sort of facts stand for themselves. A lot of these attacks were able to successfully crack a lot of hashes in this data breach. Okay, let's move on to a different example. So, something a little different, a crypto wallet example. Back in 2017, I saw that, Hashcat had support for Ethereum wallets, and I wanted to have a little look just to see if I could, create a wallet, extract the password, and crack it, just to see kind of, what it was like. Now, if the Ethereum wallets that were targeted were any of these three, Mu, Geth, and Mist. We're going to be using the MyEther wallet, the Mu one in this example. I had to go on Wayback to find out how the application looked, how the website looked when I did this, because it all looked like it was a very, creating a new wallet with a password is absolutely fine. Nowadays, it's not recommended. You shouldn't really be creating these wallets by securing them with a password. They're a better way of doing things. But either way, it generates a JSON key store file that if you have access to, you can extract the hash from, and then you can try and crack that. Now, Scrypt is what's used here, and Scrypt is really, really resilient to attack, much like Bcrypt. And Scrypt is the example of this memory-bound algorithm that we talked about way sort of back in an earlier video. So really, really painful to attack. And unless you've got quite an easy or weak password, you're probably not going to have too much success with this. So the first kind of blog I did on this just showed how, looking at the JSON file, we have all the elements here that we need to extract for our password attack, for our hashcat attack. We need the ciphertext, the salt, and the MAC, and some of these numbers here are very, very interesting. Okay, we're going to be looking at these more in a second. The ability for us to crack this depends on N and R typically, and also what we're going to find is that we're going to hit hardware limitations with GPU cracking. So there might be times when we actually have to crack with a CPU, and that's what we're going to look at in a second. How can we identify whether we can crack these Ethereum wallets with a GPU or not? Well, first of all, we need to calculate the memory required to do it. So there's a few steps involved in doing this, and the architecture and model of your card will also play a part in its ability to crack a given Ethereum wallet or not. The first thing we need to do is we need to work out how much memory is required to calculate a single computation on your GPU. This is GPU memory, not physical memory. And we can do that by taking 128 times the value of R and then timesing that by the value of N. Okay, so R and N being these values over here from our JSON key store file. That's the amount of memory for a single computation. Then we need to work out how many parallel computations we're going to spawn, because the beauty about graphics card is we can spin up loads of these sort of shader cores and other things that will allow us to run things in parallel and get, you know, all of the horsepower that these GPUs can provide. So we need to work that out, and to do that we need to work out the number of threads per compute unit, which is going to be dependent on your architecture, and then the number of compute units as well. So you can see here in the bottom right, we've got an NVIDIA and an AMD box, which gives us these required figures, and we'll look at that in sort of in situ in a second. The last thing is to multiply them together, and you get the amount of RAM required on your GPU to actually crack these hashes. So if we plug the numbers into that, we'll take a modern graphics card, an RTX 3090. We can see here an RTX 3090 has a stream multiprocessor count of 82. Okay, so that's going to be the number we plug in step 2 in a second. But let's have a look first of all. If we look at step 1, we can see here that we've got 128 times 8. Great, these were the values of R multiplied by the value of N from our JSON file, and that gives us a memory requirement of 1 megabyte for a single computation on the GPU. Okay, no problem so far. Threads per compute unit 1. Okay, so NVIDIA has 32 threads per compute unit, and AMD uses 64 in their cards. So we need to now work this out. The number of parallel computations is therefore going to be 32 because we've got an NVIDIA card, and 82 here is the number of stream multiprocessors. Okay, so the number of compute units. NVIDIA referred to their number of compute units by stream multiprocessors. And then we get a number of 2,624. Okay, so timesing this out, we get just over 2.5 gig per GPU. Now, luckily for us, that's fine because the RTX 3090 has more than 2.5 gigs of memory. Okay, it's got 24 gigs of memory in this instance, so we're all good. We're clear sailing. We can attack this Ethereum wallet using an RTX 3090. However, if we look at a wallet that was from sort of summer last year, 2021, we can see the value of N has increased quite substantially. Okay, and plugging in the same figures, we still have the same 128 meg to start with, but now when we the same 128 meg. We now don't have 1 meg, we now have 128 megs. That's definitely not the same. We now have a 128 meg memory requirement to spawn a single computation. And we're multiplying that out for the same card. We now have a 328 gigabyte RAM requirement for the GPU, which of course won't work. So you'd absolutely see unpredictable behavior, hanging blue screens, whatever you might see, that won't run. So we would need to look to crack this on a CPU rather than a GPU. Luckily, Hashcat supports that, and by using the -D switches, we can tell Hashcat to look for CPU hardware on your system. The uppercase D is the device type of CPU, so we assign that first, and then we need to assign the actual device ID. So in this particular instance, I've used the CPU on my laptop, which is device 4, so this would be dash upper D1 dash lower D4, and that would use my CPU. Of course, your hardware will differ, and you can get Hashcat to tell you what hardware it identifies based on what drivers and runtimes and things you've got installed, of course, by running Hashcat dash uppercase I. That will show you what hardware is running in the background. So if we put that through the paces, this is mode 15700. We then put our much more modern Ethereum wallet through with a higher N value, and you can see that running on a CPU, it will of course crack, but it will take quite a long time to crack. And this is just a vanilla RockU dictionary. So unless it's a very easy password in RockU, you're really not going to get too much luck with this. You can see, I would never suggest applying rules to an Ethereum wallet. And if you did, you certainly wouldn't apply one rule anyway, because it's a really, really big rule set. But just to kind of show you how slow and painful this might be if you tried to do it. Okay, so on to non-ASCII characters. Much earlier on in this training, when we looked at brute forcing and things, we discussed about the 95 printable ASCII characters when we're talking about exhausting key spaces and things. Well, if we include extended ASCII, we can get up to 256 characters. Now, ASCII uses single byte encoding, which means we only need 1 byte to store our character. An example here being, here's our alphabet, ABC, Latin alphabet, which is hex 41, 42 and 43. So we've got individual bytes here that are being stored. However, when we look towards UTF-8, that can store characters in anywhere from 1 to 4 bytes of encoding. And here's an example of that. The Greek alphabet uses 2 bytes here, CE92 for the Greek capital letter beta, for example. And if you go on to sort of further, more Eastern languages and sort of certainly certain Asian languages and things, a lot of them use up to 3, and there are some very extreme ones that use 4 characters as well. So we can attack foreign characters, we can attack foreign language with Hashcat, but we need to tell Hashcat that we're going to be attacking in hex to do this, and we can do that with the hex charset switch. So let's look at an example of that. If we wanted to attack an Arabic password, for example, Arabic uses the following UTF-8 hex characters. And there are plenty of tables you can go to look this up. An example was shown here on the previous slide as well. But if you go to a resource, you'll find that the Arabic alphabet uses 2 bytes. The first byte is always going to be one of these 4, and the second byte is going to be one of these. Now, there's clearly several hex characters here, but we can tell Hashcat to attack all these in positional requirements by using custom masks, custom character sets. We can say, here's an MD5 of a hash. And in custom character set 1, create a mask containing only these 4 hex bytes. You can just sort of paste them into the Hashcat command line, they don't need spaces or anything. Create a second custom character set containing all of these individual hex bytes. Make sure you give Hashcat the hex charset switch, and then we can apply our mask. We need to, of course, run this in brute force mode as well. But you'll see our mask here goes 1212, and that's because for each individual Arabic character, we need to, of course, store these 2 bytes. So for every 12, we're going to take a single byte from here, one of the bytes from here, and that will represent a single Arabic character. So in this mask of 10 characters here, we're actually only going to be attacking 5 Arabic characters because of the 2 byte requirement for storage. And here we have a quick video demonstrating just that, using the exact hash we saw in the slide just there. We pass that to Hashcat. That's going to run through. It's going to recognise that we're attacking in hex because of the hex charset switch here. And without too much of a wait, you can see that's cracked. It's printed we've printed the Arabic characters to screen there, and then just for the sake of the demo, we can then paste that directly into Google and give yourselves a pat on the back. Well done, because you've just managed to crack an Arabic password. So that takes us nicely onto our next challenge, exercise 13, emoji attack. Who said you couldn't crack emojis? Not us. Okay, so exercise 13 is just an MD5, but it's an emoji password, and the password is 4 emojis. Interesting. Okay, we are going to bring Callie into view. I'm going to grab the attack string required for this. Okay, and using an online resource, I've gone and looked at the UTF-8 tables to see which UTF-8 characters can be used for an emoji attack, and emojis will actually use 4 UTF-8 bytes. So yeah, we're into the realms of crazy length password, crazy kind of custom character set passwords here. Here is a hash, which is the hash taken from exercise 13, which is already on your Callie boxes. attack mode 3 for brute force, and then we're going to define 4 character sets. For emojis, the first 2 hex bytes are only going to be F0 and 9F, and this is actually based on the UTF-8 character table from this earlier slide. So if there are, I mean, there could be more extensive references out there with emojis that I haven't had covered in the slide. I'm not saying this is 100% exhaustive, but based on this table here, this is what we're looking at for this exercise. The first byte is always F0, the second byte is always 9F, the third byte could be any one of these 4 bytes, and the fourth byte could be, well, any one of these. We tell Hashcat we're attacking in hex, and now, unlike the earlier example of Arabic passwords where we only have 2 bytes, we now have to specify 4 for a single emoji. So that the first 4 characters of that mask there, those first 4 positional requirements are only a single emoji. As we're attacking a password that's 4 emojis in length, we're going to have this 1, 2, 3, 4 times, which is what you can see we've got here. So we've got a 16 character mask in total, but that only represents 4 emojis. We're going to optimize that to try and eke out a little bit of speed from Hashcat. We're going to run that, and look at that. We're getting emojis and some very interesting unprintable characters to the screen. And this shouldn't take too long. There we go. There we have it. And here, it's amazing to see. It's not something you often see in Hashcat, I know. We have our hash and our 4 emojis that have been successfully cracked. Okay, so this was our attack. And the password, as you can see, with those 4 emojis, and this particular password does represent the 4 stages of someone realising you crack emojis. First of all, they just laugh at you, then they're just unimpressed, then they're shocked, and then it's boss mode. So well done if you managed to do that. Hopefully you enjoyed that exercise, and look forward to seeing you in the next video.